We present NeuralCoMapping, a multi-robot active mapping approach that aims to complete scene map construction in minimum time steps. Constructing the map of indoor environments is of great importance to a wide range of applications in the computer vision and robotics communities. With the fast development of range sensors, many scene mapping approaches are developed to empower scene traversal by human operators with handheld sensors. Yet incomplete or unaligned scene maps are common flaws for inexperienced users due to the noisy and unstable scan trajectory. To alleviate the inconvenience of human-operated traversal, there emerges autonomous map reconstruction via active sensor movement, also known as active mapping. Previous research works in this field mainly focus on using a single robot, which is time-consuming to scan large-scale environments. In this paper, we study the problem of multi-robot active mapping. Provided the depth observations and the corresponding camera poses from all the robots, we aim to coordinate multiple robots for complete map construction of an unknown environment in minimum time steps. We first show the pipeline of our entire framework. Provided the depth observations and the corresponding camera poses from all the robots, we employ a mapping module to construct the global occupancy map. With the constructed map and provided robot positions, the global planner estimates the optimal goal positions for all the robots for efficient and complete map construction. Next, the local planner decides a moving trajectory from the robot to the goal position, followed by an action controller to perform the specific actions. Such a planning cycle is iterated until meeting the termination criterion. The key to the multi-robot active mapping problem lies in the goal position estimation to enable more efficient robot movements. There are two categories of approaches in this field. The first one is the frontier-based exploration, which decides the goal position from a set of frontiers, which is defined as regions on the boundary between open space and unexplored space. By moving the robot to the frontiers, the scene map can be completely constructed. However, these approaches are mostly myopic that hinder the time efficiency. The more recent reinforcement learning solutions directly regress the goal position via CNN, but do not guarantee the complete map construction. In this paper, we propose a novel multi-robot active mapping algorithm that takes advantage of both approaches for more efficient and complete map construction. To be specific, we reduce the multi-robot active mapping problem to bipartite graph matching, which establishes node correspondences between two graphs, denoting robots and frontiers separately in our case. The key issue for bipartite graph matching lies in the computation of the affinity matrix between two sets of nodes. The traditional frontier-based approaches can be considered as handcrafting the affinity matrix with the geodesic distance between robots and frontiers, which limits the time efficiency of active mapping. In our algorithm, we propose the global planner that learns the neural distance optimized by maximizing the long-term value that favors time efficiency and map completeness via reinforcement learning. To achieve this goal, we introduce a multiplex graph neural network, MGNN. It firstly builds two self-graphs that denote the robot and frontier information separately, and a cross-graph that establishes the dense correspondences between robots and frontiers. Then it applies the intergraph operation and intergraph operation to the two types of graphs respectively to learn the affinity between robot and frontiers. To encourage consistent robot movements and discourage the redundant traversal over explored regions, we further enhance the MGNN with two sets of new nodes, history robots and history goals collected in the past planning cycles. Then we obtain the affinity matrix by extracting the directed edge features in the MGNN, which is further solved by a differentiable linear assignment layer to obtain the goal position for each robot. We optimize the MGNN together with the differentiable linear assignment layer by punishing unnecessary time steps and rewarding the coverage increment via reinforcement learning. We compare our algorithm with several state-of-the-art multi-robot active mapping approaches and adapted reinforcement learning baselines. Experimental results demonstrate the superior performance and exceptional generalization ability of our algorithm on various indoor scenes when only trained with 9 indoor scenes. Thanks for your attention.